Welcome back. In the last video, we explored how a plain LLM becomes an AI agent, the loop that makes it agentic, and how agents plan and reason through chain of thought, react, task decomposition, and reflection. If you haven't watched that yet, I'd recommend starting there. But thinking is only half the story. An agent that can plan and reason but cannot act is still trapped inside a text box. In this video, we'll give agents hands, memory, and teammates. Let's start with tools, where an agent stops talking and starts acting. Tools are what give agents their superpowers. With them, it can search the web, run code, query databases, send emails, and much more. Think of tools as the agent's hands. They let it reach out and interact with the world. The technical mechanism behind tool use is function calling. For example, the user asks, "What's the weather in Paris?" Instead of guessing and generating text directly, the model call getWeather with city equals Paris. The system executes that function against a real API, gets the result, and feeds it back to the LLM, which then crafts a grounded response. Under the hood, tools are defined as JSON schemas in the system message. Each schema specifies a tool's name, description, and parameter types. On the execution side, code running outside the model parses the JSON output, dispatches the call to the actual function or API, and injects the result back into the conversation as a new message for the LLM to process. Here's what a real tool definition looks like in OpenAI's API format. You define a tool with a type of function, a name like getWeather, a description of what it does, and a parameters object specifying each argument's type and whether it's required. When the model decides to use a tool, its response includes a tool _calls array, each entry containing the function name and a JSON string of arguments. Your code then calls the actual function and sends the result back as a message with the role tool. This back and forth is handled through the same API. No separate endpoint needed. Modern LLMs also support parallel tool calls. If the user asks, "Plan my trip to Paris next week," the model can return 3 tool calls at once: getWeather, search flights, and find hotels. You execute all of them in parallel, send all results back together, and the model composes a single response. This dramatically speeds up multi-tool tasks. Agents can use many types of tools. Let's look at the most common ones. Information retrieval, search engines, knowledge bases, and document retrieval systems. These let the agent find facts it doesn't already know. Code execution, interpreters, and sandboxes that let the agent write and run code. APIs, external services like weather APIs, flight search, email, and calendars. These connect the agent to real-world systems. Databases, the agent can query structured data, look up records, and even write data back. File systems, reading, writing, and managing files. The agent can create documents, process spreadsheets, and organize data. In practice, agents rarely work with a single tool. They often need to work across many tools, each with its own API, schema, and data format. So, how do agents connect to them all in a consistent way? That is exactly the kind of problem a standard protocol is designed to solve. MCP, the Model Context Protocol, is rapidly becoming the universal bridge between agents and tools. To understand why MCP matters, consider the problem it solves. Before MCP, every tool integration was custom. If you wanted the agent to use a search tool, you wrote a wrapper function, defined its JSON schema, and wired it into the agent. Want to add a database tool? Write another wrapper. Want that same tool to work with a different agent? Rewrite the wrapper to fit the new agent's format. With M agents and N tools, you end up with M multiplied by N custom integrations. A combinatorial nightmare that doesn't scale. MCP solves this with a standard protocol layer, like how USB lets any device connect to any computer. A tool developer builds an MCP server, a small process that exposes the tool's capabilities through a standardized interface. The server declares what tools it offers, what resources it can provide, and what prompt templates it supports. On the other side, the agents implement an MCP client that can discover and connect to any MCP server. Once connected, the agent can call the server's tools as if they were native, no custom wrapper code needed. The architecture works like this. The MCP server runs as a separate process. either locally or remotely, and communicates with the agent via JSON RPC over standard I/O for local servers, or HTTP with server-sent events for remote servers. When the agent starts, the MCP client connects to configured servers, sends a tools list request to discover available tools and their schemas, and injects those schemas into the LLM's tool definitions automatically. When the LLM decides to invoke one of those tools, the system sends a tools call request through the MCP client to the appropriate server, gets the result, and feeds it back, all transparently. What makes MCP particularly powerful is that both sides work independently. A tool developer publishes one MCP server, and it instantly works with Claude, ChatGPT, Copilot, Cursor, and any other MCP-compatible agent. An agent developer implements the MCP client once, and it can instantly connect to thousands of community-built servers for databases, APIs, file systems, cloud services, and more. Instead of M multiplied by N custom integrations, you get M plus N. Each side only implements the protocol once. This is why MCP adoption has exploded. Major AI labs, IDE makers, and tool developers have all converged on it as the standard. So now agents can connect to any tool through MCP. But when dozens of tools are available, how does the agent pick the right one? It comes down to the LLM's reasoning. Given the user's request and the descriptions of available tools, the LLM determines which tool, if any, is the best fit. For what's the weather? It selects the weather API. For what's 17 times 384? It picks the calculator. For find recent papers on AI agents, it uses web search. Sometimes the answer doesn't require any tools at all. What's the capital of France is something the LLM already knows. A good agent recognizes when to use tools and when to just respond directly. The selection mechanism works because the MCP client has already discovered each tool's name, description, and parameter schema, and injected them into the LLM's tool definitions. The model compares the user's request against those descriptions and picks the best match, or none at all. This is why writing clear, specific tool descriptions is critical. Vague descriptions lead to wrong tool choices. Some advanced systems also use semantic similarity scoring between the query and tool descriptions, or a dedicated routing model that classifies the query before the main LLM runs. There's a practical limit to how many tools you can give an agent at once. Each tool definition takes up tokens in the context window. With 20 to 30 tools, you might use 2,000 to 5,000 tokens just for tool descriptions before any conversation even starts. Beyond about 50 tools, accuracy starts to degrade. The model gets confused by too many similar options. The solution is dynamic tool loading. Instead of giving the agent all tools up front, a lightweight classifier first identifies which category the query falls into, then loads only the relevant 3 to 10 tools for that category. This keeps the context lean and tool selection accurate. Tools give agents superpowers, but those powers also introduce real risks. Because tools do more than read files and data, they can take action on them. An agent with access to email, file systems, and databases can cause real-world damage if it makes a mistake, or if it's manipulated through prompt injection, where malicious instructions are hidden in the data the agent reads. Well-designed agents use 3 key guardrails. First, sandboxing. Code runs in an isolated container, not on the main system. Second, permission scoping. Each tool gets only the permissions it actually needs. And third, human-in-the-loop confirmation for high-stakes actions. Like, the agent wants to send an email to 500 people. Approve or deny. These guardrails are essential before deploying agents in production. So agents can now plan, reason, and use tools to interact with the world. But there's a fundamental gap. Every time a conversation ends, the agent forgets everything. It has no idea who you are, what you discussed, or what you prefer. Without memory, every conversation starts from zero. Memory is what transforms a stateless agent into a persistent, personalized assistant. And this isn't a design choice, it's a hard constraint. LLMs are stateless by nature. Each call is completely independent. The model has zero memory of previous calls. If you send "my name is Alex" in one call and "what's my name" in the next, the model genuinely doesn't know. What feels like memory in a conversation is actually an illusion. The application resends the entire conversation history with every single request. The messages array grows with each turn, and the model isn't remembering. It's rereading the whole transcript every time. The simplest form of memory is the context window, the amount of text the LLM can see at once. Modern LLMs have context windows of 200,000 tokens or more. That's enough to hold hundreds of pages of conversation. Everything inside this window the model can reference directly, but context windows have limits. In a very long conversation, earlier messages eventually fall off the edge. The model literally forgets what was said at the beginning. Think of it like a whiteboard with limited space. You can keep writing, but eventually you have to erase the oldest notes to make room for new ones. Technically, every message in the conversation, system instructions, user messages, assistant responses, and tool results, is converted to tokens and concatenated into a single sequence. The model processes all of them at once. When the total token count approaches the limit, the system must decide what to drop. Simple approaches use a sliding window, removing the oldest messages first. Another subtle issue is that even within the context window, LLMs don't pay equal attention to everything. Research has shown a lost-in-the-middle effect. Models tend to recall information at the beginning and end of the context well, but struggle with content buried in the middle of a long sequence. This means simply stuffing everything into the context window doesn't guarantee the model will actually use it. Strategic placement of important information at the start, system prompt, or near the end, recent messages, significantly affects recall quality. There's also a cost dimension. LLM APIs charge per token, both input and output. A 200,000 token context window means you're paying to reprocess the entire conversation with every message. A 50-turn conversation might use 10,000 tokens, and you're paying for all 10,000 on every subsequent turn, not just the new message. This is why context window management isn't just a technical constraint, it's an economic one. Efficient memory management directly reduces API costs. To work around the context window limit, agents use conversation summarization. As the conversation grows, older messages are compressed into a concise summary. The user is Alex, a software engineer in New York planning a trip to Paris with a $2,000 budget. We've already booked flights. This summary takes up far less space than the original messages, freeing room for new conversation while preserving the essential context. The implementation typically uses a rolling summarization approach. Every n turns, say every 10 messages, the agent makes a dedicated LLM call. Summarize the key facts, decisions, and user preferences from this conversation so far. The resulting summary, typically 200 to 500 tokens, replaces the older messages, which might have been 3,000 to 5,000 tokens. That's a 10x compression ratio. The trade-off is information loss. Summaries are lossy by nature. Subtle details, exact numbers, or the user's specific phrasing can get lost in compression. A good summarization prompt explicitly asks the model to preserve user preferences, key decisions, exact numbers and dates, and any commitments made. Some systems keep the last 5 to 10 messages verbatim for recency, while summarizing everything older, giving the best of both worlds, detailed recent context plus compressed long-term context. For true persistence, remembering things across conversations, days, or even months, agents use long-term memory backed by external storage. When the agent learns something important, your name, your preferences, a decision you made, it writes a memory note and stores it in a database. At the start of each new conversation, the agent retrieves relevant memories. This is powered by vector databases like Pinecone, Weaviate, or Chroma, the same embedding technology we explored in the LLM series. Memories are converted to vectors, stored and retrieved by semantic similarity, so the agent finds the most relevant memories even if the exact wording differs. The technical pipeline works like this. When the agent decides to store a memory, it passes the text through an embedding model, like OpenAI's text embedding 3small, which converts it into a high-dimensional vector, typically 1,536 or more floating point numbers. This vector captures the semantic meaning of the text. Similar concepts produce similar vectors regardless of exact wording. The vector is stored in a vector database, alongside the original text as metadata. At retrieval time, the agent embeds the current query into a vector using the same embedding model, and the database performs a nearest neighbor search, finding stored vectors with the highest cosine similarity to the query vector. If the user says, "What airline did we book last time?" the system finds the stored memory booked Air France flight for $450, even though the wording is completely different, because the semantic meanings are close in vector space. This is the same Retrieval-Augmented Generation pattern used across many AI applications. The top K most relevant memories, usually 3 to 10, are retrieved and prepended to the conversation context as system messages. The LLM then generates its response with these memories available, but it doesn't know they came from a database. They look like any other part of the conversation. So far, we have covered context window, conversation summarization, and external storage. In a well-designed agent, all three of them work together. Working memory, the context window, holds the current conversation and immediate task state. It's fast, but limited. Short-term memory, summarized conversation history, preserves context within a session without overflowing the window. Long-term memory, external vector storage, provides persistence across sessions. Preferences, facts, and past experiences are always available. When a new message arrives, the agent retrieves relevant long-term memories, loads the conversation summary, and combines them with the current context. The result is an agent that truly knows you and gets better over time. Here's what the final context window looks like when all three memory layers are assembled. At the very top, the system prompt with the agent's instructions and personality. Next, retrieved long-term memories. 3 to 5 relevant facts pulled from the vector database. Then, the conversation summary, a compressed version of everything discussed so far. And finally, the last 5 to 10 raw messages, the most recent exchanges in full detail. The LLM sees all of this as a single continuous prompt and generates its response accordingly. Total token budget might be 1,000 for the system prompt, 500 for retrieved memories, 800 for the summary, and 8,000 for recent messages. About 10,000 tokens total, leaving the vast majority of a 200K context window free for the model's response and any tool results. So far, we've focused on what a single agent can do, but in practice, some tasks are just too complex or too broad for one agent to handle well. Imagine building a full software application. You need to gather requirements, design the architecture, write the code, run tests, and deploy, each requiring different expertise. A single agent trying to do all of that hits a wall, the context window bottleneck. It needs all those tool definitions, all the accumulated results, and all the domain-specific instructions loaded at once. The context fills up fast, tool selection accuracy drops, and the model starts losing track of earlier steps. The solution? Just like humans form teams to divide complex work, agents can too. Split the work into specialists, a researcher equipped with search tools to gather information, a coder with code tools to develop and debug, a reviewer focused on catching bugs and ensuring quality. Each agent carries a focused, compact context, only the tools and instructions it needs. Less noise, better performance. In a multi-agent system, each agent is specialized. It has its own role, its own tools, and its own expertise. A planner agent coordinates the team, breaking tasks into subtasks and assigning them to the right agent. A researcher agent excels at finding information, equipped with web search and document retrieval tools. A coder agent specializes in writing and debugging code. A reviewer agent checks the work of others, analyzing code for bugs, verifying facts, and ensuring quality. Each specialized agent is configured with its own system prompt and its own tool set. The researcher's system prompt says something like, "You are a research specialist. Use the search and retrieval tools to find accurate information. Always cite your sources." The coder says, "You are a coding expert. Write clean, tested code. Follow the project's coding conventions." By narrowing each agent's role and available tools, you get more focused, higher quality outputs than a single general-purpose agent trying to do everything at once. You can even use different models for different agents. The planner might use a powerful reasoning model like GPT 5.4 for complex planning. The coder uses Claude Opus, where code quality matters most. The researcher runs on Claude Sonnet, fast and capable enough for search and retrieval. And the reviewer uses Claude Haiku, a lightweight model that's perfect for checking work at low cost. This model mixing strategy optimizes for both quality and cost. You use expensive models only where they matter. There are several ways to organize multi-agent teams. Let's look at the 3 most common patterns. Sequential pipeline. Agents work one after another like an assembly line. The planner creates a plan, passes it to the researcher, who passes findings to the coder, who passes code to the reviewer. Each agent builds on the previous one's output. Hierarchical delegation. A supervisor agent sits at the top, delegating tasks to specialist agents below. It decides who does what, collects results, and makes final decisions. Think of it like a project manager directing a team. Collaborative discussion. Agents communicate as peers, debating, critiquing, and refining each other's work. A coder proposes a solution, a reviewer challenges it. The coder revises, and they iterate until both agree. This mirrors how real teams brainstorm and improve ideas. In practice, orchestration is implemented using state graphs, directed graphs where each node represents an agent or a decision point, and edges define the flow of data between them. A state graph might look like start planner, researcher and coder in parallel, reviewer. If rejected, loop back to coder. If approved, end. The controller tracks which node is active, routes messages between agents, and handles branching and looping logic. Frameworks like LangGraph, AutoGen, and CrewAI have emerged to handle orchestration, each taking a different approach. LangGraph, from LangChain, models the workflow as a state machine. You define nodes, edges, and conditional routing in code with full control over the flow. AutoGen, from Microsoft, focuses on conversational agents that talk to each other. You define agents and let them have a multi-turn discussion to solve problems. CrewAI takes a role-based approach. You define agents with roles, goals, and backstories. Then, let a crew coordinator assign tasks. The choice depends on your use case. LangGraph for complex custom workflows, AutoGen for collaborative problem-solving, CrewAI for quick setups with role-based teams. For agents to work together, they need a way to communicate. This typically happens through structured messages passed via a shared message history or a message queue. A shared message history ensures every agent can see what's been discussed, just like a team chat channel. Messages can be different types: tasks, results, feedback, or status updates. Under the hood, messages are typically structured dictionaries with fields like sender, recipient, type, and content. The shared message history acts as the orchestration backbone. Each agent reads relevant messages from the history to understand its current task and the team's progress. This is often implemented as a shared state object, a central message store that all agents read from and write to. A key design challenge is context management across agents. Each agent has its own context window, and you don't want to dump the entire team's conversation into every agent's context. That would be wasteful and confusing. Instead, the orchestrator selectively passes only the relevant subset of messages to each agent. The coder receives task requirements and the researcher's findings, but not the reviewer's internal notes about a previous task. This selective context injection keeps each agent focused and prevents context window overflow. Let's see a multi-agent system in action. The user requests, build a weather dashboard web app. The planner agent breaks this into sub-tasks: design the UI layout, build the backend API, implement the front end, write tests. The researcher agent looks up the best weather APIs and front-end frameworks, reporting back with recommendations. The coder agent writes the back-end code, a simple API that fetches weather data, and then the front end, a clean dashboard with charts and graphs. The reviewer agent examines the code, finds a missing error handler, and sends feedback. The coder fixes it. The planner agent confirms all subtasks are complete and delivers the final result to the user, a weather dashboard built by a team of AI agents. Multi-agent systems represent a powerful paradigm shift. Instead of building one massive do-everything model, we compose specialized agents, each an expert in its domain, and let them collaborate. This is more scalable, more reliable, and easier to improve. Upgrade one agent, and the whole team benefits. The future of AI isn't a single superintelligence. It's teams of agents working together, solving problems that neither humans nor individual models could tackle alone. The engineering challenge ahead is reliability at scale. Each agent in a multi-agent system has a certain failure rate, maybe 5% chance of producing a wrong result on any given step. Chain 4 agents together and the combined failure rate compounds. Techniques like output validation, retry logic, consensus voting, multiple agents independently solve the same task, and we take the majority answer. And human-in-the-loop checkpoints are all being developed to make multi-agent systems production-ready. We're still in the early days, but the progress is accelerating fast. That's it for today. Like and subscribe so you don't miss more AI deep dives. See you in the next one.